seconds, 1 second. Dimmi tu quando è buono. Ok, non toccare lo zoom quando sei a posto. E blocca anche la macchina. Quando poi c'è la mia comanda è a metà. Ok.
The Second World War really gave American academic scientists their first taste of big science. It gave them money and equipment and resources that they could only have imagined in the 1930s. Before the Second World War, American academic science was pretty small scale, really string and sealing wax kind of science. It was not uncommon to have a budget for an entire university department of a few $100s for the entire year. And the Second World War drew academic scientists into these large-scale projects, Los Alamos, the MIT Radiation Laboratory, the Chicago Metallurgy Laboratory, and it gave them a chance to use money to manage science in a way that they'd never done before. It's very difficult to realize that they were coming out of academic departments of a few people into projects that involved hundreds and sometimes thousands of people. And all of a sudden, for the first time, they were given a chance not only to do science on a scale that they'd never imagined before, but to see the practical results of that science move from the laboratory into prototype, into production at an industrial contractor, and out into the field. And it was an exhilarating experience for many of them. And for most of them, it was the kind of experience that they wanted to carry back into peacetime. And when they wanted to leave these laboratories, they wanted to take a little of the MIT Rad Lab with them back to Berkeley or back to Stanford or back to the University of Chicago and recreate that exhilarating experience in peacetime, to have the same kind of budgets and scale and that same kind of birth to production process that they'd experienced during the war. So it was a time that changed their perspective on what you could do as an academic scientist. And it brought big-scale science into universities. Instead of using national laboratories to do military research during the war, which other countries did, the United States, under people like Vannevar Bush, decided it would be more efficient to keep those military projects in academic laboratories. And so the contracts were sent to Berkeley and to MIT and to the University of Chicago, rather than being done in military laboratories. And that set the pattern really for the post-war world, where much of military R&D, or at least much basic or so-called basic research for the military, would be done not in the military's own laboratories, but in academic ones. And of course that had tremendous implications both for the military and for the university.
Stop. Fare un primo piano. Regia, è partito? Okay. So can you repeat what you just told me about when or how did change the relationship between the university and the science department with the Second World War?
Sure. The Second World War changed the way the military thought about the American university, and it changed the way American scientists thought about doing science and the way that science could be done. Back in the 1930s, very few departments had more than a couple of $100 in their research budget for any one department at any one time. And it wasn't at all unusual to find in a physics department with a budget of only a few $100s a year, something like that. The military, for its part, was very skeptical about the ability of academic scientists to contribute much to the national defense. They were considered impractical and simply not very well acquainted with practical military requirements. But the Second World War transformed that relationship entirely. Academic scientists were brought into military projects like Los Alamos and like the MIT Radiation Lab, where microwave radar was invented. And they proved themselves quite efficient at turning out military hardware, and the military came away impressed with the ability of academic scientists to contribute to the national defense. It was, after all, academic physicists, for instance, who gave the nation the radar which won the war and the atomic bomb which ended it. And they were important academic contributions across the whole spectrum of military hardware. Academic scientists, for their part, got their first taste of big science. For many of them, the exhilaration of working in a laboratory where you could command thousands and maybe millions of dollars, where you had a staff not of 4 or 5, but of several thousand. The Rad Lab at one time, for instance, had a staff of 4,000, was an experience that they didn't forget, and it enabled them to do things that they could never have imagined before. And most of them returned to their home universities, back to Stanford or Chicago or Harvard or MIT, convinced that this was the wave of the future and that good science in the future was going to require these kind of budgets. And the only place where that kind of money was going to be available was going to be from the military. So it transformed both universities thinking about themselves and the militaries thinking about universities. And so that what happened really was a partnership of universities, the military, and industry, which after all, during the Second World War, had to produce the hardware that the academic scientists were inventing. And many of them, in fact, many of the academic scientists worked closely with RCA and with Bell Labs and with the other industrial contractors that produced the radar and the bombs and the proximity fuses. And so they got well acquainted. They made a strong circle of contacts which would set the stage for post-war contracts that would remake the American university.
It did change also the way of doing research within scientists and engineers. I mean, it did change their paradigm of their way of thinking.
The Second World War, let me start again.
Okay.
The experience of working with these new kinds of budgets and new kinds of equipment opened up all kinds of opportunities for post-war science and engineering. And people on wartime projects recognized that well before the end of the war, that afterwards there would be opportunities to use microwave radar components or new Geiger counters or new kinds of engineering to do science, not to create weapons this time, but to use these technologies to measure fundamental properties of nature, to use microwave tubes to accelerate subatomic particles, to use the implements of war now to do peacetime science. And so there was the expectation that you could take this tremendous resource that had been built up during the Second World War and transform it into first-rate science afterwards. So that yes, there was certainly no question that they expected that you could use these new tools of science which had been developed, say a reactor, which was a brand new tool at that point, had just been created at the University of Chicago. You could use that nuclear reactor now to do fundamental physics. You could use microwave radar not for detecting enemy aircraft anymore, but as an accelerator to do particle physics. You could use radar components to detect the change in population of subatomic particles, things like that. So you could do a whole host of new kinds of science with the technologies that have been built up for weapons research.
And you were saying to me before that the peak was not reached with the Second World War, but it was reached later on. Can you explain me this concept?
If you looked at a graph of funding for university science, federal funding for university science, and you started it in the 1930s, you'd see very, very little support for academic science until about 1940. Then you would see a sharp increase throughout the war years to unprecedented levels of federal support. Then afterwards, you'd see a sharp decline for a couple of years. There was the expectation after the Second World War on the part of both academic scientists and the military that the partnership that had been cemented during the war was coming apart, that academic scientists would go back to doing things the way that they had done before the war, and that the military would become much smaller as it had after the First World War. And so there was a period of 3 or 4 years right after the war when everyone expected a return to normalcy, if you want to term it that. But it was really the Korean War in 1950, in the summer of 1950, that re-cemented that partnership of industry, the military, and the university, and made it permanent. It was really the mobilization for the Korean War from 1950 to 1953 that transformed the relationship between the military and the university and the military's industrial contractors, and made it a permanent one, or at least one that would last through the end of the 1960s.
What about the effect on society? I mean, the social effect of such a relationship?
The partnership of the university, the military, and industry has had a number of implications for all three partners. For the university, it's meant fundamental changes in the science and engineering programs at many leading institutions of higher education. It's hard to imagine, for instance, that Stanford would have claimed its place among the elite universities of the world without the influx of military money that came there after the Second World War, and particularly with the Korean War. Stanford's reputation was really built with the military contracts that came there for microwave electronics, for traveling wave tubes and klystrons, for different research in physics and linear accelerators. Stanford's reputation was really built on those kind of defense contracts. Similarly with MIT and many other institutions, it's hard to imagine that their science programs would have been anywhere near as prestigious today if it hadn't been for that money. On the other hand, because of the military money, those programs were skewed in some directions instead of others. Military money doesn't flow evenly to universities. It flows into some kinds of programs at the expense of others. And what happened is that military funding distorted university research programs so that some parts of the university benefited enormously where others were hurt, both because money didn't flow there or because it flowed unevenly from one to another. So the impact on the university was that some kinds of programs flourished, others did not. There was another kind of impact too, which is that military funding tended to train a generation of scientists and engineers who were very good at some kinds of engineering and not very good at others. It tended to train one or at least, say, two generations of academic engineers for whom cost was no object, for whom high performance counted more than anything else, who were very good at military technology and not so good at civilian technology. And I think that left an impact on American industry. Just as military contractors tended to become addicted to the cost plus contracts of the Pentagon, so too did American academic programs become addicted to that military money with similar consequences.
Do you think that there were any spin-off because of the military research in the civilian sector? I mean, was the military, okay.
One of the long-standing arguments for large defense budgets and spending large amounts of military money at universities is that there will be spin-off into the civilian sector. Generally, that's not been true. The requirements for military technology and civilian technology are generally too different. Military technology demands high performance, high cost solutions. Civilian technology tends to put more emphasis on cost. If we look carefully at the origins of something like Silicon Valley, which is considered one of the great American economic success stories, you realize that it's really not so much spin-off from civilian technology that accounts for the success of Silicon Valley, but rather the spin-off from military programs at Stanford. Stanford and Silicon Valley both were built with defense dollars, and both became very heavily dependent on them throughout the 1950s into the 1960s, and in fact, are still heavily dependent upon them. The largest employer in Silicon Valley is still Lockheed Missiles and Space, which relies almost entirely on defense money. So that even when there appears to be a civilian spin-off, the creation of Silicon Valley or the creation of Route 128, a closer look suggests that these are actually as much a product of defense spending as the success of the universities which made those economic regions successful in the first place.
What do you think is going to happen today with, we were talking before about a new situation because of the new relationship between Soviet Union and United States and so on. Do you think
It's-
it will be easy to recycle somehow this huge investment, or what?
It's going to be very difficult to take apart this partnership of the Pentagon, industry, and the university. There are large numbers of people and institutions that have strong interest in maintaining that partnership, and it's going to make it very difficult to convert universities and industry to civilian technology. Even if there's a large cut in defense spending, there are going to be a number of people and institutions fighting to make sure that those dollars are still flowing to universities like Georgia Tech or Carnegie Mellon, which are now heavily dependent on defense spending. Georgia Tech has been an interesting example in that, like Stanford, they seized on defense money as a way of building up their reputation in science and engineering in more recent years. In fact, the late president of Georgia Tech, Joe Pettit, was in fact a Stanford man who'd come up the ranks there, saw that one way to build a great university these days was to get large defense contracts and the spin-offs into industry that come with them. He put the same program into effect at Georgia Tech with similar results. That is, a university whose reputation has soared, but which has become very addicted to defense dollars. About 3/4 of its R&D budget, its sponsored research budget, comes from the Pentagon. Carnegie Mellon also has depended very heavily these days on defense spending, especially in its computer programs, and has been one of the aggressive lobbyists for defense spending for universities. There are a number of places, Silicon Valley being one, Texas being another, which are so dependent on defense spending for universities and especially for industry that it's going to be very difficult on those economies to cut back defense spending. It's been said that Texas has always been a one-crop economy, first cotton, then oil, and now defense. And it's going to be very difficult and a lot of dislocation to try to redirect that spending in other ways. There's been talk from time to time about conversion. That means taking resources like MIT's Lincoln Laboratory, which is really devoted to air defense, classified research, and using it to investigate civilian technologies of one sort or another. But it's very difficult because they simply aren't very compatible. It's not very easy to take people who've spent an entire lifetime working on microwave electronic defense systems and tell them to work on transportation technology, or to tell people who've worked on defense computers to now work on civilian technologies, civilian semiconductors. There just isn't that much sharing of technology anymore. Each is too specialized. Again, one depends very heavily on high-cost, high-performance solution. The other depends very much on economic solutions. And so it's going to be very difficult, I think, to break this long-time pattern. It's been going now for 35 or almost 40 years, and it's going to be very difficult to change that. To do so, I think, is going to require a political consensus that we have to stop setting industrial policy through the Pentagon and start setting it somewhere else.
Do you believe that because of this, there is in society, or maybe only within the university, a kind of defense culture or something like this?
Certainly many of our top universities, as well as many of our top corporations, have become heavily dependent on defense dollars. And it's very difficult to change that way of thinking. What's happened is that over the last 40 years, 2 generations of engineering students and scientists have come through programs in which most of their professors were heavily involved in defense contracts, where the textbooks that they were educated with were written by professors who were primarily doing defense-related work, where their theses were sometimes classified and nearly always oriented toward defense projects. And they've become part of the defense culture. And that sets the direction for their careers for 20, 30, maybe a whole lifetime. 20, 30 years, maybe an entire lifetime. And so they come to see the world through the eyes of the defense culture. They become very much part of the military-industrial complex, as it's been called. And it's very difficult for them to see the world in any other way. I don't think we recognize the extent to which your graduate training determines the future direction of your entire career. And people who are, as graduate students, part of defense contracts move naturally into the defense industry. They move back and forth between industry and the Pentagon, maybe into university positions, and it does develop a separate culture, and it's very difficult to change that culture. Yes.
C'è ancora Nastro?
Siamo a 20 e 25.
Ok, possiamo andare. Which one is, from your point of view, the relationship between science and technology? And did the relationship change with the Second World War or not?
One of the lessons that engineers drew from the Second World War is that scientists could often be better engineers than engineers. That many of the great engineering breakthroughs of the Second World War were done by people who were trained in the physical sciences, physicists, chemists. Engineering educators came back to campus afterwards convinced that engineers should be trained like scientists. There was an entirely new discipline called engineering science, which was devoted to making engineering education much more like scientific education. That's at least the way engineers read it. The long-term consequences of that may have been to create worse or to educate less efficient engineers, people for whom design didn't count for very much, for whom anything that couldn't be expressed as an unambiguous equation wasn't worth considering. I think actually our engineering education was weakened by the emphasis on science that was put into the engineering curriculum after the Second World War. Engineering and science have traditionally been distinct. They're still distinct. They're separate communities with separate traditions, and when engineering tried to remake itself in a scientific image, I think it did itself and the country depended on it a disservice.
Well, what about, competing today on the international market? Okay, since because of this, of the military involvement, the big corporations, they are not anymore able to compete on the international market. Why they are still pushing and lobbying in order to have money from the military complex?
In many industries, electronics being a prime example, American competitiveness has been hurt by the military connection, by becoming addicted to defense contracts. Many electronics corporations these days complain that they're at an unfair advantage compared with their Japanese competitors because Japan spends more government money on research and development than the United States does. In fact, that's not true. The United States government spends more and has spent more than the Japanese on electronics R&D. The difference is that the money in this country is spent primarily in the military sector, and in Japan it's spent almost entirely in the civilian sector. There is no defense industry there. And the consequences of that have been enormous. What's happened is that in a number of electronics firms and whole subsectors of that industry, we have companies very good at military electronics and completely unskilled at civilian application. They tend to be very good at high performance, high cost solutions and very poor at creating things for the civilian market where cost and production engineering is so crucial. So we have companies that are very good at radiation hardened computers that can't compete with the Japanese in the civilian market. And I think we could extend that to a number of other industries. The machine tool industry is another where our government has subsidized the industry very handsomely. The problem is that it's been subsidized by the Air Force, which has very particular requirements for machine tool technology. They want technologies that can do very specialized operations, which means that they're very high cost machine tools. Nobody else except the Air Force and its defense contractors needs that kind of precision. And so our machine tool industry has lost ground very, very rapidly to Japanese and German competitors. And that same story could be shown across the spectrum of technologies. where we tend to be very good at a very narrow kind of defense contracting and not so good at civilian applications.
No, from your aspettiamo 10 secondi. 5. Okay.
There's no question that the legacy of the Second World War, of the Korean War, of the Cold War was a very sophisticated, world-class science. The linear accelerator at Stanford, for instance, was a direct spin-off from military hardware that was developed really for detecting airplanes, microwave tubes that were good for advanced radar systems. You can use the same technology to accelerate electrons, which Stanford physicists did, and they created the largest and one of the most productive linear accelerators in the world, what's called SLAC. There are a number of other examples of that kind of spin-off from defense university contracts into world-class science. The question is, what about the opportunity costs? What about the kind of science that doesn't get done? It seems to me that what's happened is that we've skewed our scientific efforts in certain directions at the expense of others. High energy physics received substantial funding, and we've done very well there. Other fields in physics, solid state physics for instance, have similarly benefited. But the question is, have we achieved those results at significant costs in doing other kinds of science? Not only science which would benefit the civilian economy more, but science that has interesting questions of its own. There are kinds of physics, rational mechanics, things like that, that just don't get done anymore. The old, even aspects of theory are neglected in the pursuit of science that is effectively done for military ends. So I think that we have to consider more the opportunity costs of military science than we perhaps have.
Oh, can you tell me something a little bit more, and also if you can give me an example on the relationship between the military complex and the university? Starting with the Second World War or with the Cold War?
You'll have to explain a little more what you're looking for.
Well, an example
Of the symbiosis between them?
Yeah, between the three. I mean, the military, corporation, and university.
Okay. One of the best examples that I know of the partnership of the military, the university, and industry is the special relationship between Lockheed and Stanford. In the 1950s, the early 1950s, Stanford Aeronautical Engineering was really going downhill. It had once been a great program, but had really fallen on hard times. It was down to a couple of professors and a couple of master's students, and that was about it. At the same time, Lockheed Corporation was falling on hard times as well. It had once been a fairly flourishing enterprise during the war, but afterwards it tried and failed in the civilian market. As one of its presidents said, there's money in commercial aviation, we know because we put it there. They were losing money at a terrible rate and decided that the only way they could save their corporation was really to go after defense contracts, particularly ballistic missile contracts, because that's where the big money was. And so they moved, actually, in order to compete, they thought that they would have to create their own university because you needed scientists and engineers on the cutting edge of aerospace engineering to be able to compete. So they tried to set up their own university in Southern California and really failed miserably. After a year, the man they chose to direct it, a former Air Force general, quit, and he took most of their top people with him. So what Lockheed did was move their entire missiles and space division to what we now call Silicon Valley, to be near the Ames Research Center of what NACA, the predecessor of NASA, and to be near Stanford. If they couldn't make their own university, they would go into partnership with one. What they did is, what Lockheed did was arrange with Stanford to name one of their missile consultants as the new head of their division of aeronautical engineering. they sent several corporate employees to Stanford to teach, some part-time, one full-time. They began sending their corporate employees to Stanford to take their degrees. Many of Stanford's graduate students would be full-time workers at Lockheed who would get their educations part-time on something called the Honors Cooperative Program. So they were actually corporate employees taking their degree at Stanford. What happened is you developed very close relationships between faculty and management, between students and employees. And Stanford, of course, benefited enormously. Its aerospace or aeronautical engineering program went from being nearly its aerospace program went from 2 faculty members to a couple of dozen, from 2 master's candidates to dozens of graduate students, from $4,000 a year in sponsored research to millions. It went from being nothing to maybe the top aeronautical engineering program in the world. At the same time, Lockheed went from near bankruptcy to being one of the wealthiest corporations and also, not coincidentally, the #1 defense contractor in the United States by the 1970s. And so certainly both Stanford and Lockheed benefited in many respects from that close relationship. They both depended on those defense dollars, Lockheed for industrial contracts, Stanford for academic ones. But the cost of that was an aerospace program at Stanford and a corporate program at Lockheed that were both totally dependent on defense contracts. And if you look at the kinds of research that Stanford people are doing in the 50s and into the 60s, you find that almost all of their work in one way or another is directly related to the particular challenges of ballistic missiles, of the very high temperatures that you face, of guidance systems, things like that. And so aeronautical engineering, instead of being devoted to civilian technology, to safer aircraft, to fuel-efficient engines, to something like that, is devoted instead to ballistic missile technologies, to shooting up, bringing back down, and guiding a ballistic missile, and a ballistic missile. So there the opportunity cost can only be measured in what didn't happen in civilian aviation, where there's virtually no spin-off. You just don't need to go Mach 20 with an airliner. But instead of concentrating on fuel efficiency and safety and other things that would be of benefit to the civilian market, well, Stanford and Lockheed devoted themselves to military challenges.
Oh, you were telling me before that during the Second World War, this investment of money into the university became very big, and it was a period that was called classified research. That's what you said to me.
Yes.
Right?
Yes.
Let me ask you something. I mean, this period of classified research, it did bring also a new way of doing research, because I mean, if you are not doing research for the sake of research, because I mean, as an intellectual challenge, you know, I think also it did produce within the university a kind of a classified culture. You know, can you tell me something about this? I mean, if you have anything in mind.
No. Classified research was part of World War II, of course, classified university research at MIT, at Los Alamos. But after the war, it pretty much disappeared for 4 or 5 years. There were very few classified contracts. It's really with the Korean War that classified research became a normal part of doing business at the university. It was during the Korean War that the Defense Department asked universities like MIT and Stanford and other places to take on large classified contracts. What these classified contracts did was essentially take the basic research that the universities had already been doing and extend it, so that now, instead of just looking at basic problems in microwave electronics, universities would actually be designing prototypes of countermeasures tubes for jamming enemy radar, say. And sometimes they were actually producing the prototypes, then working with industrial contractors to manufacture those tubes. What makes it all a classified culture, if you want to call it that, is that not only do faculty members have to have security clearances to work on this kind of project, so do graduate students. And in fact, at Stanford, at MIT, some theses, some dissertations were even classified, which means that, of course, a graduate student would write a thesis that a number of faculty members who didn't have security clearances couldn't even read. And this is a challenge to the longest and strongest traditions of the academy, which require openness, public scrutiny. And this provoked quite a controversy later in the 1960s during the Vietnam War, when this classified research was revealed for the first time. But it's surprising that during most of the 50s, this was taken as a normal part of doing business. And academic scientists convinced themselves and convinced their colleagues that it was important to do classified research because otherwise you couldn't stay on the cutting edge of technology. That if faculty members and graduate students didn't have security clearances, they would not be aware of some of the most important research in electronics, in aerospace, in physics, and in other fields. And it became, to a surprising extent, the normal way that academic engineering and other sciences were done.
Were there any resistance within the university during that time?
To a surprising extent, there was no protest and no controversy about taking on these classified contracts. Universities were eager to do so for the most part, administrators and faculty members alike. There were occasional complaints that the classified programs might end up being the tails that wag the academic dog, and in large measure that was true. But there was surprisingly little complaint until much, much later. Largely, I suppose, because most of these faculty members had just come through one world war. They were now involved in another war in Korea, and they saw this as an essential part of university service. And they didn't stop to consider often the long-term implications that this might have for academic tradition.
One last question. Well, you were saying that Texas, it's, I'm saying that Texas is booming because of the space industry and the military.
And defense, that's right.
The same is for California and Silicon Valley and so on.
Same is true for Massachusetts,
Right.
yes.
So in a way, it's absolutely true that defense or war bring wealth and in a way push the economy.
There's no question that certain regions in the United States have benefited enormously from defense spending. Silicon Valley, Route 128 were both creatures of the Pentagon, creations of the Pentagon. They depended on military funding for their creation, and they've depended on military funding pretty much ever since, in the same way that Stanford and MIT depended heavily on military contracts. Texas is another good example of an economy that depends very heavily on the military. Yes, Route 128, Silicon Valley boom when defense booms. They also bust when defense budgets are cut. The Massachusetts miracle shrivels very quickly as soon as Defense Department budgets are down. The other cost is more difficult to measure, but American steel, American automobiles, parts of the economy that are not doing well in part because of patterns of federal support which have gone to the defense industry instead of others. While we have subsidized our electronics industry very heavily and aerospace very heavily, we have not done the same kind of thing with other sectors, and they're withering. What's happened is we have booming regions which have large defense contracts and defense industries, and other parts of the country which are doing very poorly because of the skewing of our federal spending priorities.
Tell me something about the relationship between this kind of technology and workers and labor. Because it seems to me that the only people that are not making any money out of these billions dollars coming from the defense, it's the workers. What do you think about it?
Ironically, nearly every region in the United States wants to become like Silicon Valley. You can hardly find any regional planner, urban planner, who doesn't want to clone Silicon Valley for his own city or his own region. Everyone wants to copy the Massachusetts Miracle. What they don't recognize is that high-tech development benefits a few, but it tends to replace, in established regions, $25 an hour steelworker jobs, union jobs, with $5 an hour non-union assembly jobs. There's a polarization in places like Silicon Valley between management, scientific, engineering workers and assembly workers. Many of the workers in Silicon Valley are in fact recent immigrants or immigrant labor. The pay rates are very low, and if anything, it exacerbates the distance between labor and management. I think that's not widely recognized. It tends to, just as defense spending tends to favor some regions at the expense of others, so it tends to favor some workers, that is management, scientific, and engineering workers, at the expense of others. It creates jobs, but ones that tend to be fairly low paying. And unfortunately, Silicon Valley ends up being a very expensive place to live, which means that those workers have to commute long distances to be able to afford housing at all.
Oh, do you also believe that this involvement of the military, it did produce also in the management, in the big corporation in the United States, a new way of thinking about production and the relationship also with labor? I mean, a new concept also of discipline, you know, within the plant.
Let me think for a second.
Yeah, sure. I mean, if you have to say something, otherwise.
Yeah.
You know, my point, what we have been learning and also thinking is that because historically, from the arsenal, the interchangeability of parts, and also because of the Second World War, industrialists have been always thinking of being able to apply a kind of military discipline into the factory, where, okay?
Yeah. Since the end of the Second World War, one of the important priorities of the Defense Department has been to reduce the dependence of defense contractors on labor, particularly organized labor, and to, wherever possible, replace recalcitrant workers with machines. The feeling is that you can more effectively mobilize your industrial resources in the event of war if you don't have to worry about the possibility of a strike, something like that. That's been true in machine tools, as David Noble has shown, but it's also been true in the electronics industry as well. One of the major government efforts in the early 1950s was something called Project Tinker Toy, and the idea was to be able to create electronic components by machine, so that you didn't have to rely on individual workers to solder together components, so that they could be manufactured from raw materials to finished electronic component entirely with automation. There's no question that the whole move to automate electronics manufacturing was pushed by the Defense Department in the hopes that it would produce more of a command system over which the Pentagon would have more control. If you have to rely on workers to assemble the components, they may go on strike, they may ask for higher wages. If you can automate the entire process, you have much more control, and that's something, of course, the Pentagon has been pushing ever since. Tinker Toy, as it was called, didn't work out very well as a defense program, and it did even worse in the civilian market. There was an attempt there to use this automated manufacturing system for civilian components, but it was a disaster because, like so many military technologies, it was set up so that it was very high performance but very high cost. Civilian industry didn't want it, and so after spending millions of dollars on it, the government simply abandoned it about 1960.
Okay.
That's it.
Okay.
Academic scientists had a role to play in the First World War, but American universities did not. American academic scientists and engineers served in the First World War, but they did so in uniform for the most part. They became part of the military rather than working on contracts for the military in American universities. That's one of the major differences between the First and the Second World War. In the First World War, scientists and engineers left their universities, served in military laboratories as uniformed officers, and afterwards they simply returned to their home universities. And since they didn't like much working for the military because of the bureaucracy and whatnot, for the most part, they were glad to be out of uniform. In the Second World War, on the other hand, universities received those contracts, and so academics worked as civilians, often in their home universities or in other prestigious universities. And that set a new kind of relationship where now they were still civilians, still academics, working in a university environment, but with military funding. And that made it much more attractive than it had been beforehand. And so while there was general agreement that after the First World War, that the military and the university would each go their separate ways, afterwards there was much more of an agreement that this partnership had been effective and should be continued. And that's primarily the difference between the two wars.
Okay.
Is that all right? I'm sorry,